Hello, my name is Josh Noel, a current master's student in the MIT Han Lab, and today we present the Temporal Shift Module online Google Maps demo running on the NVIDIA Jetson Nano platform. This is the same demo as previously demonstrated running on a high-powered Windows desktop platform and supports the same exact functionality. For example, we can use the swipe gestures to navigate this overhead view. We can stop. We can also zoom out or zoom in. In addition to navigation of this overhead view, we can also enter Street View. First, by drumming our fingers to open the overlay, and then by navigating the character over a Street View location, for example, the road. Now that we're over the road, we can use the thumbs up gesture to enter Street View. Now that we're in Street View, these same swipe gestures as previous change our perspective. Further, we can use these zoom gestures to move backwards or forwards. Zoom out, moving us backwards, and zoom in, moving us forwards. Now let's return to the overhead view. First, by opening the overlay, and then by closing the overlay. Now that we're back at the overhead view, let's take a closer look at the performance characteristics of this demo. In the bottom corner, you can see two performance statistics. First, the demo runs at about 13 frames per second on the Jetson Nano platform. The processing of each frame can be broken down into three separate stages. First, the fetching of the frame from the frame buffer of the camera, which takes about 33 milliseconds for the 30 FPS webcam. And then the processing of this frame in the Temporal Shift Module network on GPU. Then, once we have the outputs of this network, they go through some post-processing on the CPU. For example, smoothing of the outputs for the purposes of map navigation. The second statistic you see is video frames per second. This is a characterization of the throughput of the second two stages discussed. That is, the input of the frame to the Temporal Shift Module network to the end of post-processing on the CPU. This 30 video frame per second throughput corresponds to a 33 millisecond latency. This latency can be further broken down into two steps. That is 13 milliseconds for inference, followed by about 20 milliseconds for post-processing. Central to the functionality and performance of this demo on the Jetson Nano is the low computation cost of the Temporal Shift Module network. Previous gesture recognition frameworks would require expensive 3D convolution operations with high computation cost. However, we extract the same information using only the computation cost of a 2D convolution with a corresponding shift. This lower computation cost therefore allows this demo to maintain full functionality and high performance on the low-powered Jetson Nano platform. For reference, this same demo running on a quad-core quadro-card laptop achieved about 77 video frames per second. However, on the $99 Jetson Nano, this demo gets about 30 video frames per second, consuming between 8 to 9 watts of power. This demonstrates the importance and usefulness of the vastly lower computation cost of the Temporal Shift Module network for running complex gesture recognition tasks on low-powered, less expensive devices.